All right, in this example, we're told that we have water vapor at a certain temperature and pressure entering a turbine operating at steady state. The water expands to 1 psia and 150 degrees Fahrenheit, and we can neglect heat transfer and kinetic and potential energy effects. Determine the turbine power per unit mass flow rate. That should be pretty straightforward. That's a first law application. Part B is what is the rate of entropy generation per unit mass flow rate. That should also be straightforward. That's an entropy equation kind of problem. In part C, we're asked to determine the maximum theoretical turbine power for the same inlet state and exit pressure. What is the outlet temperature for these conditions? That one's a little trickier. We'll come to that. I won't discuss it now, but we'll come to it at that point. And then sketch the two processes on a TS diagram. You'll notice that there are English units in this example, degrees Fahrenheit, psia. That's psia means pounds force per square inch absolute. The A means absolute. Don't worry about the units here. It just makes the unit conversions a little bit more tricky, but it shouldn't affect the problem, how we solve the problem. The picture over on the right-hand side shows a typical low-pressure turbine. What's happening here is you have, let me zoom in on it, you have steam that comes in from here, and the turbine here is designed symmetrically. So as the steam comes in, it can go off to the right or it can go off to the left. It's the same kind of geometry either way. And both turbines are attached to the same shaft. So, and you'll notice that you go through a series of small, kind of a small cross-sectional area, and then it gets to a larger cross-sectional area. And that's because the flow is expanding. That you'll notice that when it states in the problem statement that water vapor expands to 1 psia, essentially what's happening is as the pressure drops, the specific volume goes down. So that means that the volume is expanding, actually. Is that correct? I'm sorry, the specific volume goes up. I had it the opposite way. So anyway, the specific volume goes up, and so they make the cross-sectional area larger so that you don't get really large velocities. And if you want to see more about how a steam turbine operates, I recommend this video. Just click on that, and then you can see it's something like a 5-minute video. It's pretty simple. All right, let's get started. So we were going to find, let me first of all sketch what the turbine looks like. Kind of our typical schematic. Here's the turbine. There's the shaft. We have some flow coming in over here. This is our state 1. So the pressure there is P1 is 140 psia. T1 is 1000 degrees Fahrenheit. Comes out down here. State 2, there P2 is 1 pound per square inch absolute. And T2 is 150 degrees Fahrenheit. So what we're going to do is draw a control volume surrounding this turbine. Here's the power coming out. And we're going to apply the first law to that. Remember, what we're trying to find here is we're trying to find the power per unit mass flow rate. So this is a first law analysis. You've done many of these, so hopefully it should be straightforward by this point. We'll write out the first law to be complete. Again, I encourage you to do it this way. I know it seems tedious, but it's really the way to do it is you start with the basic equation in its full glory, and then you simplify it using your assumptions. And it's really the best way to communicate your solution approach. So the first term on the left-hand side is 0 because it's steady state. The mass flow rate coming in and the mass flow rate going out, when you combine those together, that's going to be an m dot h1 minus h2. And what we've done along the way here is we've neglected the kinetic and potential energy differences between inlet and outlet. We were told to do that. And then I've also used conservation of mass, which if I just work it out over on the side here, this one's pretty straightforward. Again, dm dt is 0 because it's steady state. We have one inlet, one outlet, so they're the same. We'll just call it m dot for convenience. We'll assume that the turbine is operating adiabatically. We were told that in the problem statement. And then we're trying to find the power out, so we can rearrange the equation. And then we're trying to find the power out per unit mass flow rate, so we'll divide through by m dot. So that's how we find that quantity. As far as determining those specific enthalpies, we go back to the property tables for water. And this again should be something you're very familiar with doing. This part's a little tedious, but you've done it many times. So the only difference here is that we're using English units, so you'd need to find a table in English units. The back of your textbook has this kind of a table. So there's, in the back of your textbook, the Munson et al. Book, there is a set of tables in SI units and then also a set of tables for English units. So if we look up the values here, what you'll find is this is a superheated vapor, and the specific enthalpy is 1,531.0 BTUs per pound mass. And while we're at it, I'm going to also look up the specific entropy because we're going to use this for part B of the problem. That comes out to 1.8827 BTUs per pound mass degrees Rankine. And then at state 2, we can do the same thing. So that's 1 psia. T2 is 150 degrees Fahrenheit. And if you look that up in the tables, again, it comes out to be a superheated vapor phase. H2 is 1127.5 BTUs per pound mass. S2 is 2.0151 BTUs per pound mass degrees Rankine. I know using these English units is not your favorite thing to do. It just makes one. You need to just be careful with the unit conversions. So in one way, it's a good thing because then you actually have to work out the unit conversions. The bad thing about it is it's easier to make mistakes with the unit conversions. But unfortunately, the United States still sticks with the English system. So in industry, you'll come across these kinds of units pretty commonly. We're different from much of the world. All right, so anyway, if we take these values for the inlet specific enthalpy and the outlet specific enthalpy, plug it back into our equation from the first law, what you'll get is that the power generated by the turbine per unit mass flow rate comes out to be 404 BTUs per pound mass of water. Okay, so that's part A, right? We were trying to find the turbine power per unit mass flow rate. Now for part B, what is the rate of entropy generation per unit mass flow rate? So that's going to be the entropy equation applied to the same control volume. So we'll write that down, entropy equation. Write it out in all its glory here. Okay, so there's the entropy equation. We'll simplify that using our assumptions. First term is 0 because it's steady state. The flux terms, flux just means something coming in or going out of the control volume. This will be m dot S1 minus S2. The heat transfer term is 0 because it's adiabatic. And then the sigma dot term, that's our entropy rate of entropy production. That's what we're trying to solve for. So when we rearrange this, we're going to get S dot equals m dot times S2 minus S1, or since we want rate of entropy production per unit mass flow rate, that's just sigma dot over m dot. That's just S2 minus S1. And we conveniently looked up the values for specific entropy from the tables earlier on, so we can easily plug those values in, and what we'll get is that comes out to be 0.1324 BTUs per pound mass degrees Rankine. So that's part B. Oh, and you'll notice here that obviously we have an internally irreversible process, right? So the sigma dot is not 0. It's greater than 0, meaning it's irreversible, which would lead you to think that this turbine is not operating in its most efficient manner. If it was going to be operating in its most efficient manner, then we shouldn't have any irreversibility to it. It should be reversible. But here we have some irreversibility, so it's not really operating in its most efficient manner. Okay, so that's part B. Now for part C, we're asked to find what the maximum theoretical turbine power per unit mass flow rate for the same inlet state and exit pressure should be. So we want to find the maximum theoretical turbine power. I just sort of alluded to that a moment ago. That's going to occur when we have no irreversibility, right? So that's going to occur when the sigma dot would be 0. Well, in that case, if you go back to our entropy equation and you take a look at it for a second, if we're operating at steady state, the left-hand side is 0. It's still adiabatic, and it's now reversible because we want the maximum power. So the maximum power will occur when we have no irreversibilities. So that'll be sigma dot is 0. So then what you'll see is that S2 should equal S1. We should have an isentropic process. So if we assume that it's adiabatic, and internally reversible, so adiabatic just again means the Q dot is 0, internally reversible means the sigma dot is 0, then what we're going to get, so this will lead to an isentropic flow, right? Which means that S2 is going to equal to S1 for this particular case, right? The specific entropy going out will be the same as the specific entropy coming back in. That, again, just kind of falls from this equation. If sigma dot is 0, S2 must equal S1. To show that this case is a little different from the previous one that we worked out, I'm going to put a little subscript S on the 2 here. So this is, what we're doing now is we're saying that state 2 occurs isentropically. Okay, so when we write out the first law expression for this case, it'll still be W dot out over M dot. I'm going to put a max here because we're trying to solve for the maximum. That will be equal to H1 minus H2S, right? The maximum is going to occur when state 2 occurs isentropically, when the process is isentropic. So we now need to determine what the isentropic specific enthalpy is going to be. So just recall that so if you look back at the problem statement, it says for the same inlet state and exit pressure. So the H1 stays the same, but we also have the same exit pressure of 1 psia. Okay. So we have two pieces of information. So state 2s, we know that P2 is still 1 psia, but we also know that, and this should be 2s here, the specific entropy at 2s is equal to specific entropy at 1, which when we looked it up, it was 1.8827 BTUs per pound mass degrees Rankine. Just remember that the S1 we found earlier, it's right up here, right? So for our isentropic case, it's S2S is the same value. So we now have two properties. We can look up our other properties, namely the specific enthalpy and the temperature. So when you go back to the property tables for water, what you'll find is that this corresponds to a saturated liquid vapor mixture. So it's no longer a superheated vapor, but becomes a saturated liquid vapor mixture. The corresponding temperature for that is 101.7 degrees Fahrenheit. So the temperature is dropped. Recall that the original temperature for the case where you had irreversibility, it was 150 degrees Fahrenheit, but now it's lower, it's 101 degrees Fahrenheit. Okay, and then you can also determine the specific enthalpy for this case. Here you have to do you have to calculate the quality first. Actually, let me just show you that just so it's complete. Since we're dealing with a saturated liquid vapor mixture, you have to calculate the quality. So we can find the quality using the specific entropy. So S F at 2S comes out to be this. So this is the saturated liquid specific entropy. Again, I'm getting these values from the back of your textbook. Here's the saturated vapor specific entropy. You can see our specific entropy is somewhere in between that. So we're going to have some quality. So we can calculate the quality at this state. And when you plug in the numbers for this, the quality comes out to be about 94% or so. So it's 0.94841. And then we can calculate the specific specific enthalpy from this. So here's the specific enthalpy for the saturated liquid. It's 69.74 BTUs per pound mass. Specific enthalpy for the saturated vapor is 1,105.8 BTUs per pound mass. Oops. And then you can calculate the specific enthalpy at state 2S. That comes out to be 1,052.35 BTU per pound mass. So we had to do a little work there because we're dealing with a saturated liquid vapor mixture. So now we have the new specific enthalpy, assuming an isentropic process. So that goes in our equation right up here. We still have H1 from before, that was 1531. So that goes here. So we can now calculate our maximum power per unit mass flow rate. And that comes out to be 479 BTUs per pound mass. So that's our maximum. That's the best you're going to get out of this turbine for those given inlet and outlet conditions. So this 479 you can clearly see is larger than what we had before, which was 404 BTUs per pound mass. So and again, the reason there's a difference here is the 404, we had some irreversibility, right? So it was not as efficient as it could be. The 479 corresponds to a reversible process. So that this is the maximum you're ever going to get out of this turbine. Let's go ahead and plot then what this looks like on a TS diagram. So here's because we're dealing with water that changes phase, we're going to draw our vapor dome. Let me draw an isobar corresponding to state 1. So this is our P1. That's our initial pressure of, what was it, 140 psia, I believe that was, yeah. And we were dropping down to 1 psia. And our initial state was 1,000. I think we're at about 1,000 degrees Fahrenheit. So there's our T1, 1,000 degrees Fahrenheit. This is our state 1. And then state 2, this is the irreversible case. It was also a superheated vapor. And our temperature there, this was given in the problem statement, it was 150 degrees Fahrenheit. So that's state 2. So that process looks something like this. You'll notice that the specific entropy increases in that particular case. And then our maximum power case was isentropic, so our state 2s is down here. So that path just drops vertically downward because the specific entropy at state 2s is the same as that at state 1. And then our temperature there was a little bit lower. So T2s was 101.7 degrees Fahrenheit. You can see the temperature is a little bit lower. Now the reason the temperature is a little bit lower for our isentropic case is because what's happening is the enthalpy that comes into the flow is more efficiently converted into power. So if you go back up to our first law expression, the enthalpy is sometimes called the flow energy. It's just the amount of energy contained in the flowing stream in terms of pressure and temperature. So like internal energy and the pressure work, right? That's our specific enthalpy. So the incoming flow has a certain amount of flow energy to it. And what happens is when you have some irreversibility, that enthalpy, that flow energy doesn't get converted into shaft work very efficiently. So what happens is some of the energy goes into shaft work, but then some of the energy goes into temperature, goes into increasing the temperature. So that's why we get a higher temperature for state 2, because some of that irreversibility just goes into temperature rather than going into shaft work. Whereas for state 2s, it's a much more efficient process because it's reversible, and so more of the energy, more of that flow energy goes into actually producing power. So that's why the power is higher. And then because more energy is going into the power, less energy is going into increasing the flow's temperature. So that's why you have a lower temperature there. Now the last thing that I want to do, this is a preview for some upcoming work, is we can start thinking about what's known as an isentropic efficiency for the turbine. We know what our maximum power out of the turbine could be for this situation, and then we have our actual power out of the turbine. So you can think about, how close are we to the maximum? That gives rise to an efficiency. So we can define what's known as the isentropic turbine efficiency. So here's the efficiency for the turbine, and it's the isentropic turbine efficiency because we find the maximum power using an isentropic process. That's going to be defined as the power coming out, actual, divided by the power out maximum. That corresponds to our isentropic process. So in our particular case, the actual power out was 404 BTU per pound mass. Actually, what we did is we divided both of these by mass flow rate. That's fine. And then the maximum was 479 BTUs per pound mass. So this comes out to be, when you calculate that efficiency, it's 0.843 or 84.3%. So our turbine here the actual turbine has an efficiency of about 84%, meaning that we haven't quite reached our maximum possible. Real turbines actually can be quite efficient. They can be in the upper 90% as far as the isentropic efficiency. So this one could use some improvement. We're going to talk about this topic, defining isentropic efficiencies for turbines and compressors and nozzles, coming up in a lecture or two. But this is just a little preview here. All right, we'll go ahead and end this example. I think we covered everything we needed to.